Okay, so here we are to talk about parabolas now. And you may be thinking, wait, I know about parabolas. I saw them in integrated 2. But these are parabolas that are going to be looking at them in a different way. So we're going to look at the parts that make up the parabola. So you know about the vertex, but we may not know about the focus, the directrix, and the lattice rectum. But once we know about those parts and how they all fit together, then we'll be able to derive the formulas for the parabolas. So let's first look at the definition of a parabola, because the definition is what's going to help us derive the formulas. So a parabola, by definition, is the set of all points equidistant from a fixed point, which is called the focus, and a fixed line, which is called the directrix. So what does that mean? Well, what that means is this. We're just going to look at a parabola opening up. What we're going to do could then be adapted for parabolas opening up down and left and right. Parabolas also can open up diagonally, but we're not going to look at those this year. We're just going to look at up, down, left, and right. So let's say that we have a focus. Let's just put it right there. We'll call that the focus. And then I'm going to go ahead and put a line down here, and we're going to call this the directrix. Now, halfway in between the focus and the directrix is always going to be the vertex. And it does make sense that that point would be on this parabola, because it does say, let me get my picture out of the way here. It does say the set of all points equidistant from a fixed point called the focus and a fixed line called the directrix. And if I put this point halfway in between, this point is going to be equidistant to the focus and the directrix. According to my picture, I went ahead and did it 2 units, but it could be any units, but it's 2 units from the focus and it's 2 units away from the directrix. That point that's halfway in between the focus and the directrix, that's always going to be your vertex. And then I'm just going to draw a parabola, but then we'll take a look at how this definition fits in with it. So if we have a parabola like this. Now there's an actual geometric shape to a parabola. I can't just draw any generic U shape and call it a parabola. They have a very, very particular geometric shape. If I go ahead and just pick this point, for instance, this point is equidistant from the focus and the directrix. In fact, actually, I kind of nailed it there. It looks like it's 4 units away. If I pick another point, I'll try to just make it more random. But this point right here, this distance and this distance should be the same. So this is equal to this, and this distance is equal to this. And I'll just pick one more. If I pick a point up here, the distance from the focus to the directrix, if I drew my picture accurately, those should be the same length. So that's what we mean by the equidistant. Any point on this parabola, when you measure the distance to the focus from that point and the distance to the directrix from that point, should be the same distance. And that makes a parabola. Now, one nice thing about a parabola, I'm not going to get too heavy into this, but the reason why this one point in the center there is called the focus, it's because these have 2 main applications, but there's different versions. But any rays that come in directly, perpendicular to the directrix, they will bounce off. If the parabola was a reflector, it would reflect off the parabola into the focus. So anything that comes in perpendicularly. If it comes in at an angle, it's going to bounce off and it's not going to hit the focus. So that's kind of cool. And then also, likewise, the other way, something at the focus, if there's, for instance, a beam of light at the focus, a flashlight is a prime example, or the a spotlight, one of those big spotlights that sits on the ground. If there's a light source at the focus, then anything that bounces off the reflector will bounce straight out. And that's how you can focus your beam. And if you've ever played around with one of those flashlights where you can twist the end and it kind of makes your beam wide or focuses it and makes it narrow, it's because it's moving the bulb away from the focus. If it's at the focus, that's what's going to make your beam of light focused. And then if it actually goes a little closer to the reflector, it's going to widen the beam. So that's how that works. All right, so we're not going to get heavy into that though, but that's the idea of a parabola. And that's why it really is nice in optics and acoustics, because also sound, same thing with sound. If you've ever noticed those microphones that have, there's kind of this curved, I don't know what you call it, like it's a reflector, but this curved thing behind the microphone, and it's going to take all the sound that comes in straight and then put it in the microphone to record. And so like, when you want to, when they show in the movies, like they're trying to spy on somebody and they beam the microphone at a building and they're trying to pick up on the conversations, and you see this kind of curved thing behind, that's in the shape of a parabola. If you took a parabola and actually spun it, kind of makes this bowl, that's in the shape of the parabola, and it's collecting all the sound waves and then focusing it to the focus, which is where the actual mic is. So it's kind of cool how this all works. All right, so that's what a parabola is, and here are the parts. Now there's one more part that is called the lattice rectum, and your book doesn't really focus on this. No pun intended. I like the lattice rectum because it helps you actually draw the parabola. And so I'm just going to draw another one without all these dashed lines for the distances. So if I draw another parabola here, so I'll put the directrix, and I'll put the vertex in the focus. So here's the vertex, here's the focus. And I'll draw this parabola here. Trying to draw it as accurately as I can. So the lattice rectum is a line segment parallel to the directrix that goes through the focus, and its endpoints are on the vertex. Whoa, that's a lot. It's not that bad. It's this line right here. It's parallel to the directrix. So here's the directrix. I'll put that actually down here. Parallel to the directrix. The endpoints lie on the vertex, and it goes through the focus. So that's all it is. So all you have to do is draw a parallel line through the focus, parallel to the directrix, goes through the focus. Now the reason why this is handy is because this distance, which we'll just call P, it's kind of standard to call it P. Now by the definition of a parabola, we know that that distance, the distance from the focus to the vertex, should be the same as the vertex to the directrix. So that's P. And this guy right here, the lattice rectum, the length of the lattice rectum is always going to be 4P. So if you know where the focus is and you know what P is, then you can just go half of P to the right, half of P to the left, and you got two other points on your parabola, and you really haven't done any work. So you'll see how we use that when we actually are doing some examples where we're going to graph parabolas. But that's the handy thing about the lattice rectum. So that's why I do like to cover it, even when the textbooks don't cover it. Okay, so we have these parts of a parabola. Now let's go ahead and derive the equation of a parabola. Let me scroll up a little bit. Actually, I guess I'll go to a new page. We're going to start with our parabola with the vertex at the origin. So there's the vertex. And we know we have this line here called the directrix. We have this point up here called the focus. Now here's what I was doing to draw my parabolas. I can tell just by looking at the picture P is 2. So remember the length of the lattice rectum is always going to be 4P. So if P is 2, the length is 8. So I'm going to go half that to the right. I'm going to go 4 units to the right, 4 units to the left. That gives me my parabola. I know how wide to make my parabola. So it's kind of handy. Okay, so like I said, we know that the distance is called P. So the directrix then is at y equals negative P. The focus is at 0P. And then I'm just going to put some generic point here, xy. And what we want to do is we want to find an equation to represent any point on this parabola. And we're going to use the definition of a parabola. By definition, we know that the distance from F to that point will be the same thing as the distance from that point to the directrix. I'm going to call that point P. Sorry, let's go ahead. P, xy. So by the definition of a parabola, the distance from F to P, which we can just call it that, that's the notation for the distance from F to P, that should be the same thing as the distance from P to the directrix. Oh, good thing we have a distance formula. So I'm going to go ahead and use the distance formula then to help me out with this. Actually, I'm going to leave that up there. So the distance from F to P, remember that's the square root of x2 minus x1 squared plus y2 minus y1 squared. And then the distance from the point down to the directrix is, well, that's y units. And then I have p more units that I got to go down. So it's going to be y plus p. So now I have an equation to work with. That actually right there is my equation for a parabola. It turns out I can go ahead and clean that up a little bit, but there it is. So again, the distance from the focus to any point on the parabola can be represented using the distance formula. And then this side is the distance from that point to the directrix. And it doesn't matter where the point is, you're always going to take the y-coordinate and add p. So let's see what happens when we clean this up. First, I'm going to go ahead and square both sides. Let's get rid of that square root. So I'm going to have x squared plus y minus p squared equals y plus p squared. All right, looks a little better. I'm going to go ahead now and square those quantities and see what happens. So x squared plus, and then we have y squared minus 2py plus p squared. And on the other side, we have y squared plus 2py plus p squared. Oh, and look at this. I see a y squared on both sides. We'll subtract that. And I see a p squared on both sides. We'll subtract that off. So those are all gone. Now I've got x squared minus 2py equals 2py. If I just add 2py onto both sides, now I have x squared equals for py. And that's it. That's the equation for a parabola. Now that's specifically for an equation for a parabola that opens up with a vertex at 0, 0. So this opens up and the vertex is at 0, 0.